Hello student, welcome to our physics discussion, that is physics in a smart way. In our last video, we were talking about the rectangular component method, but we are in halfway stage. We did find out the components, so-called x and y component of a vector. That was the point our progress had been. Now, we take the remaining issues connected with that. Our basic aim was, let us say we put in this in the form of a question. There are three vectors. One is A, other is B, third one is C. I have drawn many diagrams. Don't worry, if you don't understand, gradually we shall be going all those things. They show the gradual progression in which our approach should be. Diagrams will be helpful here. A makes some angle, let's say that is angle alpha. B makes some angle with y-axis, let us say that is beta. C makes some angle with x-axis, let us say that is gamma or something like that. Okay, any angle. Practically, when we are dealing with the question, the values or magnitudes of A, B, and C will be given along with the angles alpha, beta, and gamma. As you know, so far as rectangular components are concerned, one of the component will be coming as the main vector, whose component we are finding out. Main vector, one of the components will be main vector into cos of the angle, and other component of the same vector will be coming as main vector into sine of that angle. Okay, so now the issue we are in second part of that. Basically, our job was to find the resultant. So here, if the resultant vector is R, then R must be sum of A vector, B vector, and C vector. Okay, so that is the question we are involved with. Okay, so now what to do? We start with our discussion. Three vectors are shown. That is the diagram number 1 or figure number 1. In figure number 2, I have broken down A, B, and C into their components. A will be having two components. One is X, Y component of H, AY, X component of B. Oh, I have forgotten. That will be like this. That is BX. And Y component of Y will be BY. Similarly, C will be having its X component, that is CX. Y component will be downwards, that is CY. One thing you must be careful here, the directions and magnitudes of the components, they must be found out by you absolutely correct. Otherwise, nobody can save us. So now we come down to the second stage. We break all the vectors into its X and Y components. You might be wondering, array, our method is going in the opposite direction. Our analysis is going in opposite direction. Our basic aim was to combine A and B and C into a single vector. But in place of combining, we have divided A into two parts, B into two parts, or two components, C into two components. In place of combining them, the three vectors which were originally present, now we have broken them down into 6 vectors. Okay, no problem, don't mind. Our thing will be systematically sorted out, no problem. Initially, we don't bother. So after breaking down into all those things, into all those components, so what we do, we take the stock of X vectors and keep it in mind that X and Y, they stay independent. Anything happens in X direction, it can have no influence on Y direction. Anything happens in Y direction, it can have no influence on X direction. Already I had hinted that in my last video. Think about that, and we shall be discussing at a later date. So now what to do? Next step, we collect all the x component, we combine them. But mind it, components are individually vectors also. They have got directions. X is towards right, bx is towards left. If ax magnitude, let us say it comes out as, you find out as 10, bx magnitude that comes out as, let us say, 4 or 3 like that. Cx magnitude comes out as 6 or something like that. Then what to do? We combine all the x component, but that combination must be algebraic, not arithmetically. You have to be careful on the directions. So when you combine all the x components, that we write as sigma x. Sigma x means sum of all x component of all the vectors. So sigma x means that is x plus bx plus cx. Okay, with proper directions. I'm also putting a vector sign. And when you put down their value, in fact, this thing, I am just taking their values arbitrarily. If x equal to 10, and you know towards right is x positive, you might put x as 10, but bx cannot be cannot be put as 4, because bx is in negative direction. I have to put as -4. Cx, that is towards positive x direction, I can take that as +6. So in this way, you put them down, their magnitude along with their directions. So whatever it comes, you can say this as sigma x. And also with a little bit of thought, you can realize that is also the final resultant's x component, or Rx. If you do not realize, just write down as Rx. Okay, you shall be finding it yourself without any prompting from me. Similarly, you combine all the y vectors into one, and that combination or that summation of y vectors we put as sigma y. So sigma y will be ay plus by. When I say plus, it can be minus also, because in your case, you know cy is downward. So that is addition with proper sign, algebraic addition. And this sigma y will be the resultant's y component, because the final resultant is 1. Okay, so you can put them as Rx and Ry, or you can write them as sigma x and sigma y, no harm is done. So now finally, we come down to the diagram number 3. All the x components are made into 1. All the y components are made into 1. So now there are 2 vectors. One is Rx, that is Ry. This Rx also can be put as sigma x, no problem. And this Ry also, if a student likes, he or she can put as sigma y, no problem. Okay. Then we clearly realized, if you, at the last step, if you combine Rx and Ry, those will be yielding in a single vector. Combining Rx and Ry, that gives us a single vector, and that has to be the resultant. So you know how to combine them. This is Rx and that is Ry. Okay, and ultimately, when we combine Rx and Ry, we follow the same graphical method of vector addition. We find it. Now the resultant is found out. Okay, as it is, that is figure number 4. That is figure number 4. In figure number 4, we clearly see that the final resultant magnitude will be coming as, because you are seeing here a right angle triangle, that is Rx square plus Ry square. That will be immediately giving us how much is the resultant or resultant magnitude. And one thing else, only the magnitude is not sufficient to fully know a vector, and here we expect to know the resultant in the complete possible detail. We have to be aware of its direction. Here is the direction is given by angle theta. How much the final resultant makes with x-axis or positive x-axis. If we consider this triangle again and consider tan theta, we know that tan theta comes out as Rx Ry by Rx. So these last two steps, they give us the magnitude and they give us the direction of the resultant. That is the way with the rectangular components. Okay. So first of all, the methods seem to be going in mutually opposite directions. First of all, we are given some vectors. In the next step, we go in the opposite way. Opposite way means instead of combining them, we break each vector into its x and y component. Okay, so a lot of vectors will come out. In the third stage, we combine all the x components and y components. All x components, they become a single vector. All the y components, they become a single vector, that is sigma y or ry, sigma x or rx. Then in the last step, we combine the rx and ry into the resultant, knowing that Rx and Ry, they must be the resultants X component and Y component. I think it is clear to you. And as I told you before, once you get hold of a method, once you know of a new idea, or whatever it is, you must discuss the pros and cons of it. So far as the pros are concerned, positive side of this concern, unlike parallelogram rule or cosine rule, where the formula, if I am asked to repeat it again, r equal to root over of a square plus b square plus 2ab cos theta. Here in this method, there is no limit to the number of vectors that you can deal at one go. In our sample case, in our question, or in this case, I have taken 3 vectors. But if you could have taken 2 or 3 vectors more, then no problem. Our number of steps will be limited to 4 only. You break every vector into its x and y component, then collect all the x components and make it a single vector, collect all the y components, make it a single vector, and then combine x component and y component net or resultant or sigma x and sigma y into the final vector, that is the resultant. Some of you might be wondering like this, okay, but I require 4 diagrams and all those things. These 4 diagrams I have illustrated to make my case very clear so that you'll be you'll be knowing the fundamentals or the idea. You'll be having the basic idea on the issue. But every time you don't have to go through all those 4 steps, all those 4 diagrams or all that. You have to go through the steps, but not the 4 diagrams, because once you have adopted the idea or made it a habit of breaking a vector into x and y component, many things will be done in the mind. These writings you have to do, okay? Diagrams you may skip with, you may dispense with. Finally, from the first diagram, you can come down to the last diagram, skipping all those things, because Rx, how much is sigma x, or Rx, how much is sigma Ry, already you have written them. If you are proficient to in the process of breaking a vector into x and y component, if you make their directions correct and magnitudes correctly find out, of them are found out, then we'll be having no problem. So in every case, you are not required to draw all the 4 diagrams. I have drawn the 4 diagrams for your convenience so that you can easily understand this. Okay, that's all for today. next video, I'll be dealing with some cases of some peculiar cases rather of the so-called parallelogram rule and this component method which we have already discussed. Okay, they have to have the basis of your understanding on vectors and scalars, and they will be helpful. Okay, thank you again for your patience, for your understanding. That's all.